Welcome to The Explainer. Today, we're going to uncover the secret journey your words take every single time you make a call or send a message. It's a trip that happens in the blink of an eye, but it's truly one of the most incredible feats of modern engineering.
I mean, it really does seem like magic, right? 1 second, a sound is right there in your room, and the next, someone's hearing it on a whole other continent. But here's the thing. It's not magic. It's actually this brilliant step-by-step process. Think of it like a hero's journey for a tiny piece of information, and you and we're going to follow it from the very beginning to the very end.
So way before we had the ones and zeros we know today, the very first step on this whole journey was taken with simple dots and dashes. Yep, Morse code, pioneered by Samuel Morse way back in 1837. It's one of the first binary codes ever, right? A way to take complex letters and boil them down to just two simple signals to send messages over wires. And that core idea, turning our complex world into a simple, two-part language, well, that's the foundation for literally everything we're about to talk about. Okay, so our journey really begins with the first and honestly maybe the most magical step of all, translating something physical, like the actual sound wave of your voice, into something a computer can wrap its head around. We have to somehow turn a wave into a number. All right, think of this as our map for the whole trip. Every single piece of digital info you've ever sent follows this exact path. It starts at the source, goes through an encoder and a modulator, travels across the channel, and finally gets to the receiver. So let's use this map to track our little hello at each of these super important stages.
Okay, let's dive right into that first step, sampling. Now, this whole process is governed by a fundamental rule called the sampling theorem, and it makes this incredibly powerful promise. It says we can take a smooth, continuous wave, chop it up into a bunch of tiny snapshots, and, this is the amazing part, still be able to perfectly rebuild it later, but only if we take those snapshots fast enough.
So, just imagine this smooth, flowing line is the sound wave of you saying hello. It's beautiful, it's analog, which just means it's totally continuous. But see, that's a huge problem for our digital systems. Computers don't think in smooth curves. They only think in distinct, separate steps.
So, how do we translate it? Well, we take these snapshots, or samples, of the wave at incredibly fast, super regular intervals. We're basically measuring its value at thousands and thousands of specific moments in time. And just like that, that smooth curve is now represented by a series of precise, individual data points.
So, how fast is fast enough? Well, for a clear phone call, we need to take at least 8,000 samples every single second. Think about that. That's the magic number. It's called the Nyquist rate, and it's what ensures we don't lose any of the crucial information in your voice.
Okay, so now we have our data points. What's next? The next big step is to translate the value of each and every one of those points into the universal language of computers. You guessed it, binary code, the language of ones and zeros.
And this is done through a process called quantization. Now that sounds super technical, but it's really just a fancy word for rounding. See, the value of each sample could be almost anything, so what we do is we round it to the nearest value from a predefined list of levels. It's kind of like taking any color you can imagine in a rainbow and having to match it to the closest crayon in a 64-pack box. Right, and each of these levels, every single crayon in that box, has its own unique binary name. Level 1 might be 001, level 2 is 010, and you get the idea. And boom, just like that, the smooth analog wave of your voice has been completely transformed into a string of ones and zeros. Your voice is now officially speaking digital.
So our message is now in digital format, this long stream of bits. But here's the catch. It can't just float through the air or zip down a wire all on its own. Nope. It needs to be packaged up and prepared for the long trip ahead.
That whole packaging process is called modulation, and you can think of it like this. You wouldn't try to send a letter across the ocean in a little rowboat, would you? Of course not. You need the right vehicle. Well, modulation is what gives our digital message the powerful vehicle it needs for that long-distance journey. Okay, let's break it down. Think of your string of bits, that's the binary code for hello, as a secret message written on a tiny piece of paper. On its own, it really can't go very far at all. Now, think of the carrier wave. This is our powerful, tireless messenger. It's like a radio wave that's capable of traveling huge distances through the air, and it does it at the speed of light. So, modulation. That's the really clever process of encoding your message onto that carrier wave.
It's literally like attaching your little piece of paper to that super fast messenger. And that's what gives your bits the ride they need to cross the channel and finally reach their destination.
All right, our message is packaged and it's on its way. But now it's about to enter the most dangerous part of its entire journey, the channel.
So the channel, that's just the medium the signal travels through. It could be wires, fiber optic cables, or even just the air all around us. But this medium is filled with a villain, one that's trying to corrupt our message at every single turn. And that villain's name is noise. We're talking random interference, other signals, even just heat. It all adds up to noise.
And this, right here, is where digital signals reveal their superpower. See, when noise hits an old-school analog signal, it gets permanently messed up. The original information is actually damaged. But a digital signal, it's incredibly resilient. Even if noise makes the signal all jittery and ugly, the receiver just has to make a simple choice. Is this a 1 or is it a 0? It's that simple. And that robustness, that strength, is the key reason our entire world went digital.
So, after surviving that perilous journey through the noisy channel, our hero signal finally arrives at its destination. And this is where the receiver performs what feels like a kind of technological magic to bring that original message back to life. Basically, the receiver's job is to just work in reverse. It undoes everything we just did. First, it demodulates the signal, which means taking our message off that carrier wave. Then, it decodes the bits, cleaning up any damage from the noise and correcting any errors it finds. And finally, it reconstructs that sequence of data points all the way back into a smooth, continuous analog wave that's ready to power a speaker.
And just like that, the journey is complete. The data has made its full round trip, from a simple sound wave in one room to a stream of bits crossing entire continents. And now it's been perfectly rebuilt into the original sound, ready for someone to hear it.
So what's the big takeaway here? It's that every single time you speak into your phone, this entire elegant process unfolds. It's a truly brilliant solution that takes the messy, chaotic, analog world and turns it into a tough, robust digital message that can survive a journey of thousands of miles and do it almost instantly. So, from a simple wave to a string of bits, and all the way back again. This incredible digital journey is what powers our entire connected world. I mean, it's become so fast and so reliable that most of us just take it completely for granted. But it does make you wonder, right? As we get better and better at encoding more of our world into ones and zeros, what are we gaining, and what, if anything, might be getting lost in the translation?